Hello. In this video, I would like to do some problems with inductors and capacitors from Chapter 6. The first problem I would like to look at is Assessment Problem 6.1. You'll notice in the text, this problem has a video with it, and I strongly encourage you to take a look at that video. So I took a screenshot where he shows the graphs for the functions, the various functions: current, voltage, power, and energy. And so I encourage you to watch that video as well as pay attention here. So let's take a look at the problem. The current source in the circuit shown generates the current pulse as such. Okay, so we have a circuit that looks like this. And actually, no. And it has an inductor here. So this is I sub G. And the inductor has a value of 4 millihenry. And I sub G is equal to 0 for t less than 0. And it's equal to 8e to the minus 300t minus 8e to the minus 1200t for t greater than and equal to 0. So, part A, find V sub 0. Okay, in order to find V sub 0, we would have to find V of t. So we know that V of t is equal to L di dt, which is equal to 4 times 10 to the minus 3, and the derivative of 8e to the minus 300t minus 8e to the minus 1200t dt. Okay, so V of t is equal to 4 times 10 to the minus 3 times 8 times minus 300 e to the minus 300t plus 1200 e to the minus 1200t. And if we multiply all that together, get my handy dandy calculator here, 300 times 8 times 4 times 10 to the minus 3, we get minus 9.6 e to the minus 300t plus 1200 times 4 times 10 to the minus 3 times 8 is 38.4 e to the minus 1200 t. So this is our expression for voltage. And we're looking for V sub 0. So V at time equal to 0 is minus 9.6 e to the minus 300 times 0 plus 38.4 e to the minus 1200 times 0. We know that e to the 0 is 1, so this would be minus 9.6 plus 38.4. So 9.6, 38 minus 38.4 is 28.4 volts. Okay, so part B, find the instant of time greater than 0 when the voltage V passes through 0. So if we look at our graphs here, the voltage is 0 at this point where T0. And if you look at the current up here, that's where current is maximum. Since voltage is a derivative of the current, when you set voltage equal to 0, you're setting the derivative equal to 0. And we know from calculus that you can find critical points when you set the derivative equal to 0. So the derivative is the slope, and the slope here would be 0, which would make that maximum. So in essence, when we found V of 0, we are also finding the maximum current. Okay. So, excuse me, when that's equal to 0. All right, so part B, 9.6 e to the minus 300t plus 38.4 e to the minus 1200 t equals 0. And again, this would be I max. Okay. So let's put part of this on the other side. 38.4 e to the minus 1200 t is equal to 9.6 e to the minus 300 t. So let's divide by 38.4 e to the minus 300 t. So this would cancel out here, and this one would cancel out here, and we're left with e to the minus 1200 t over e to the minus 300 t is equal to 9.6 over 38.4, and this side is e to the minus 900 t is equal to, let's see, 9.6 divided by 38.4 is 0.25. And if we take the natural log of both sides, then it will cancel that out. So the natural log of 0.25 is 1.386294. Divide both sides by minus 900, and t is equal to 0.00154 seconds, which is 1.54 milliseconds. So at 1.54 millisecond, voltage crosses through zero, and the current is at its maximum value. All right. C. What are we doing? Find the expression for the power delivered to the inductor. All right. We know that power equals voltage times current. And we have expressions for both voltage and current. Our voltage expression is right here. And our current expression is right here. So let's multiply those two together. So let's move things around so we have the positive sign first. 38.4 e to the minus 1200 t minus 9.6 e to the minus 300 t times the current, which is 8. That's not very good, 8. 8 e to the minus 300 t minus 8 e to the minus 1200 t. Okay. So P of t is equal to 38.4 times e to the minus 1200 t times 8 e to the minus 300. So we'll do this, then we'll do this one, then we'll do this one, and this one. Okay. So P of t is equal to 307.2 e to the minus 1200 plus 300 minus 9.6 times 8 is 76.8 e to the minus 300 plus 300, and I'm going to say goodbye to these lines because they're all right. So now we'll do this one here, and nope, this one here. So 38.4 times minus 8 38.4 times 8 minus 307.2 e to the minus 1200 plus 1200 t, and plus 9.68 times, I'm going to guess it's 76.8. Imagine that. It is e to the minus 300 plus 1200 t. All right, so this would be 1500. This would be 600. This is 24. And this is 15. So 76.8 plus 307.2 is 384. E to the minus 1500 t minus 76.8 e to the minus 600 t minus 24. Nope. Got ahead of myself there. Minus 307.2 e to the minus 2400 t. And we always like to put things in order. So, but we like the positive first. So this is good. I'm gonna P of t. Let's go with that one. So that's our expression for power. Let's see, this is C, the expression for power. Okay, D, the instant when the power delivered to the inductor is maximum. All right, power is max. We can find max power by finding the first derivative equal to 0. So let's take the derivative of this equation. So P prime of t is equal to 384 times minus 1500 e to the minus 1500 t minus 76.8 times minus 600 e to the minus 600 t minus 307.2 times minus 2400 e to the minus 2400 t and let's see, 384 is minus 5760 e to the minus 1500 t 76.8 is plus 46,080 e to the minus 600 t plus 307.2 times 2400 is 737,280 e to the minus 2400 t, and this is equal to 0. Let's reduce this a little bit here, make it easier to read. Let's divide by 46,080 and then e to the minus 2400. So we'll divide by the smallest. 46,080 e to the minus 2400. 46,080 e to the minus 2400. And we'll do it here too. And that brings us to minus 12.5 e to the plus 900 t plus 1 times e to the plus 1800t, and plus 16 equals 0. Okay, so we need to solve for t. The easiest way to do this is to set x equal to e to the 900t. So x squared would be e to the 1800t. So if we rewrite this, it would be minus 12.5x plus x squared plus 16 equals 0. So x squared minus 12.5x plus 16 equals 0. And using the quadratic equation, which is minus b plus or minus square root of b squared minus 4ac all over 2a, we can find x. So x is equal to minus b would be 12.5 plus or minus b squared minus 4 times a, which is 1, and c, which is 16, and 2 times 1. All right, so x is equal to 11.052343, or 1.447657. And we had said up front that x was equal to e to the minus 900. So this is equal to e to the minus, or to the plus 900t. So here t is equal to 2.67 milliseconds. And solve for t, and t is equal to 0.000411 seconds, which is 411 microseconds. All right, so P, the power first reaches maximum value at 411 microseconds. So let's take a look here. So right here, it's 411 microseconds. Where else is it 0? Right here, where it crosses over. Okay, let's see. Looks like we need to add another page here to finish this problem. Okay, so we found E, the maximum, the time when power is maximum. Now let's look at the instant of time when the stored energy is maximum. Okay, if we scroll back up here, or we can see at time t naught, energy is maximum. And it is maximum when current is maximum. So for inductors, energy is at the maximum level when current is at the maximum level. So we found the maximum current in part B is at t equal 1.54 milliseconds. All right. So our equation for energy is 1/2 Li squared. And we're looking for maximum. So let's see, the instant of time when the stored energy is maximum. We said that that was 1.54. Okay, so now we're on G, the maximum energy stored in the inductor. All right, so maximum energy stored is equal to 1/2 the inductor, which is 4 millihenry, so 4 times 10 to the minus 3, and I max squared. So I is 8 times e to the minus 300 t, which is 1.54 milli, minus e to the minus 1200 times 1.54 milli. And this will be squared. So let's solve for this here. The maximum value for I is 1200, 1.54 times so this would be 3.78 amps. Okay, 3.78 squared times 4 milli divided by 2. And W max is equal 0.028577 joule, which is equal to 28.58 millijoule. Oops. Okay, that concludes 6.1. Now let me turn the page to assessment problem 6.2. This is with a capacitor. All right. The voltage at the terminals of the 0.6 microfarad capacitor shown in the figure is 0 for t less than 0. So voltage and 40 e to the minus 1500 t sine 30,000 t for t greater than or equal 0. And we can redraw this to look like this. And the voltage, or the current, I. Okay, so first part. Find I of 0. Okay, we know with capacitors, I equals C dV over dt. So for t less than 0, I equals 0.6 microfarads times the change in 0 over dt. Oops. So for I equals 0 for t less than 0. Okay, so for t greater than and equal to 0, I equals 0.6 times 10 to the minus 6 times the derivative of sine 30,000. Oh, no, more than that. I'm just gonna derivative of, I'm going to have to write small, 40 e to the minus 1500 t sine 30,000 t over dt. So I of t, let's change colors here. I of t is equal to 0.6 micro times 40, and the derivative of e to the minus 1500 t is minus 1500 e to the minus 1500 t times sine 30 plus e to the minus 1500 t times 30,000 sine 30,000 t. So I of t, you know what? Oops, the derivative of sine is cosine. Okay. I'm going to move things around here. (0.36 e to the minus 15 sine 30,000 t. So let me look at the original problem here. Find I of 0 for, okay, so I of 0 here, I of 0 is equal to 0.72 e to the minus 15,000. You know what? We're going to, oh well, times 0 cosine of 0 minus 0.36 e to the minus 15,000 0 sine of 0. And I of 0, so this is 1, this is 1, this is 1, this is 0. So I of 0 is equal to 0.72 amps for t greater than or equal to 0. So I want to point out something here, and that is that I of 0 minus is equal to I of 0 plus. Or is it the opposite? V of 0 minus is V of 0 plus. So this would be I of, 0 plus. I of 0 minus does not equal I of 0 plus. But V of 0 minus does. Okay. So that's part A. Part B. Find the power delivered to the capacitor at time of pi over 80 milliseconds. Okay, so we have an expression for I of t, and let's see, I'm going to change the color here and circle it. It's right here. Let's simplify that a little bit. So the expression for I of t, we could say, let's pull E minus 1500 out. Times 0.72 cosine 30,000 minus 0.36 sine 30,000. Okay. So we know that power is voltage times current. And we have an expression for voltage and we have an expression for So let's find voltage at pi over 80 milliseconds. And let's find current at pi over 80 milliseconds. Okay, so voltage at pi over 80 milliseconds is equal to 40 times e to the minus 15 times sine 30,000 and we would get 22.1941961 times 0.923879,533, which is 20.505 volts. All right, let's find the current at pi over 80 milliseconds. So we wrote this as e to the minus 15 times 0.72 cosine minus 0.36 sine and I of pi over 80 milliseconds is equal to minus 31.66 milliamps. So P equals P of pi over 80 milliseconds is equal to 20.505 volts times minus 31.66 milliamps, which is minus 649.24 milliwatts. All right, part C. Find the energy stored in the capacitor at T equals pi over 80 milliseconds. All right, so with capacitors, we know that pi over 80 milliseconds, which is equal to 1/2 the capacitance times the voltage at pi over 80 milliseconds squared. So that would give us 1/2. The capacitance is 0.6 microfarads and our voltage is 20.505, and that's squared. So that would give us 126.137 microjoules. I think I'm going to stop this video here, and I will continue recording more problems after this video. I don't want to have these videos too long.